All right, here we go with Chapter 9 Homework AB Review. This is a combined assignment that includes all of the Chapter 9 topics, and it's also the last one we'll do this whole semester. The average this week was 9.74 out of 12, as you'll see here. Hard to compare that to previous years because we used to have 2 Chapter 9 assignments. This year we combined them into 1 because of the week that we lost, but it seems like it's a pretty good outcome overall for everybody. So we're going to go through 3 major topics in this review. So Chapter 9 has a lot of different things covered, and one of the major ones at the beginning was Intermolecular Forces, IMFs. It seems like we did pretty well on those. I don't think there's really any questions that deal with that specific topic. We can certainly talk about those at another time if you have any questions about that. But we are going to go through a few different types, namely classifying substances, especially different types of solids that we might have. We're going to talk about a little bit with the cubic crystal structures for metals, and then finally we'll end with phase diagrams, which is the very last topic in this chapter, the very last topic we cover in this whole course. So we do have one question about intermolecular forces. So again, we did pretty well for these on the most part, but this was a true-false question where we basically about 50% of people got it right, and that's always a little bit alarming because you could, close your eyes and do it and get the same results. So let's see what happened here. So this problem deals with dipole-dipole forces result from instantaneous dipoles that form in atoms and nonpolar nonpolar molecules. So we have to recall that for intermolecular forces there are 3 types, and we should understand a little bit about, first of all, which types of substances have these intermolecular forces, and then a little bit phenomenologically about what they actually are. And so if we look at the 3 different types, most of the problems you're going to have to do, and actually that would help in this problem too, is you just want to know what kind of substance has these. So if you're talking about London dispersion forces, you're talking about anything that's nonpolar. So that's going to be noble gases or nonpolar molecules. Now it's true that anything in the world has London dispersion forces, so that's always going to be there. But if you're talking about which substances only have London dispersion forces, or where that's the most important intermolecular force, it's going to be anything nonpolar gases, noble gases, nonpolar molecules. All right, that's going to be those substances will only have London dispersion. Dipole-dipole forces occur in anything that's polar, and so we learned back in chapter 4 how to determine whether a molecule is polar or nonpolar, and that's going to distinguish whether they would only have London dispersion forces or would have London dispersion and dipole-dipole forces, with dipole-dipole being the stronger and then more important force. And then hydrogen bonds is a special type of dipole-dipole interaction where you basically, anything that has OH, NH, or FH bonds. So if you have a molecule that has one of these or more than one of these bonds in it, that will be polar, so it will be, but when it's an OH, NH, or FH bond, it's especially polar. Hydrogens are very small, so they can pack together very closely, and we call that hydrogen bonding, which is essentially just a stronger dipole-dipole interaction. There's no real distinction between these except for the types of molecules that are involved. Now that's kind of distinguishing which substances would have these. The other thing to think about for this problem is sort of phenomenologically what happens. So in London dispersion forces, you have what's called instantaneous dipoles. So London dispersion forces, again, they can involve nonpolar substances. So the substances that would only have London dispersion forces, they're not going to have permanent dipoles, but what instead happens is you get what's called an instantaneous dipole, which is where for a very short period of time, the electron distribution distorts, it's no longer symmetric, and then you're going to create a small dipole that's going to interact with other nearby dipoles and influence them. And so London dispersion forces, you have instantaneous dipole interactions. Dipole-dipole forces is when you have permanent dipoles interacting. So that would be something like HCl, which has delta plus, delta minus, as we talked about way back when we introduced polarity. And then this is going to interact, for example, in this way with another HCl, where the opposite charges sort of line up with each other, and you have this electrostatic interaction involving these permanent dipoles. And then finally, for hydrogen bonds, as we said, it's just a special type of dipole-dipole interaction. So it's going to look a lot like this over here, just with the more electronegative atoms, oxygen, nitrogen, and fluorine participating. So if we look at this problem here, it says dipole-dipole forces result from instantaneous dipoles that form in atoms and nonpolar molecules. This one is going to be false, because if we're talking about instantaneous dipoles and we're talking about nonpolar substances, that would only be the London dispersion forces. So you cannot have dipole-dipole forces if your substance is nonpolar, and furthermore, dipole-dipole forces involve permanent dipoles, not instantaneous dipoles. So hopefully that's clear. I know that was kind of a long-winded summary of those three forces, but there is going to be, a question both on the third midterm and the final where you have to distinguish between these three forces and know some things about them. So we want to make sure that we're clear on how those are. All right, the next few topics deal with different types of solids. So the one here, again, another true-false one where we had close to a 50% success rate, was atomic solids generally have low melting points. So atomic solids is sort of a broad characterization. So we talked about in the lectures some of the classifications of solids. And there's different ways of distinguishing them and then the different properties that they have. Atomic solids is sort of a classification that's going to involve two types. So it's going to involve metallic solids, and it's going to involve what are called network atomic solids. So the definition of atomic solid, which I should have said earlier, is that an atomic solid is a solid that only has one type of atom, meaning that all atomic solids are elements. Now, not every element exists as an atomic solid, but there are, as we said, two types that do. So metallic solids, all metals are going to be classified as metallic solids, so that's a subcategory of atomic solid. And in this case, what we want to think about, if we're talking about melting points of different types of substances, is what are the forces that are holding together the atoms in these types of solids. And in metallic solids, you're going to have the metallic bonding, as we call it, the sea of electron model that's holding all the atoms together. Network atomic solids are going to be some nonmetals. There's not too many that actually would fall in this category, but the classic one is going to be really both forms of carbon would be classified as network atomic solids. So diamond and graphite, really this whole group 4, and then silicon, germanium. These elements that occur in group 4, and perhaps some of the ones around them, would also sort of fall in the category. These are network atomic solids, so they don't form molecules like many of the other nonmetals do. So we know that a lot of the nonmetals form molecules like N2, O2, F2, Cl2, all those diatomics, P4, S8. A lot of the nonmetals form molecular solids, but in some cases, carbon being the most common example, they form network atomic solids. And in these substances, the atoms are all held together by covalent bonds. Okay. So in both types of substances, there are relatively strong bonding interactions, either metallic bonds or covalent bonds, that are holding the atoms together. And then what that means is, if we talk about the melting points of these, for metallic substances, they tend to be moderate to high melting point, and network atomic solids have very high melting points, because in order to melt these substances, you have to break these strong bonds between the atoms, and that would result in them requiring a lot of excess energy, a lot of high temperature to be able to melt them. So atomic solids are generally going to have high melting points, and so this would be a false statement. Really, the only type of solid that has low melting points would be the molecular solids. So that would be things like ice, frozen water, or any of the non-metal elements that exist in molecular form, if we cool those down to a solid, like solid nitrogen, for example, or I2, which is a solid naturally at room temperature, those molecular solids would have low melting points because they just have weak intermolecular forces holding them together. But for metallic solids and network atomic solids, the two types of atomic solids that we have, you're going to have medium to, in most cases, high melting points. All right, this question here also deals with metallic bonding, what we sort of introduced a little bit on the last one. It wants to know which of these statements concerning metals is incorrect. I think there were answer choices that gave different combinations of these three choices, but we'll just go through them. So in the solid state, metals conduct electricity uniformly in all directions. And so the key thing about metallic bonding is that you have, it's often referred to as a sort of sea of electrons model. And what that means is that you're going to have the valence electrons in metals are going to be delocalized over the whole surface of the metal, over the whole piece of the metal, really the whole volume. And so there's going to be electrons that are shared between metal atoms going in all directions, very delocalized. And so what that means is that when you have conductivity in metals, you tend to have conductivity in all directions because the electrons are delocalized in all directions. They're not just along one axis, or they're not localized between two atoms, they're just delocalized everywhere. And so you can conduct electricity or do thermal conductivity, a related topic, in all directions. So this one would be true or correct, so we're looking for the incorrect one here. And then this one is sort of stands in contrast to that. The bonding in most metallic solids is monodirectional. And when we talk about this metallic bonding, it's going to be, again, as we said, delocalized over the whole metal in all directions. All right, so it's no longer the picture that we introduced back in chapter 3 where you just have two atoms sharing two or more electrons between them. In metallic bonding, you have electrons that are shared really over the whole piece of metal, freely moving throughout the substance, and that's sort of then not really a directional model, but as we said, it goes in all directions, and that leads to electrical conductivity in all directions. So this one's going to be false because monodirectional means in a single direction, but metallic bonding goes in all directions through the solid. And then finally, the electron C model explains electrical conductivity of metals by assuming that their valence electrons move freely within the lattice. And this is what we've really been talking about in this problem. The electron C model is the idea that the valence electrons are delocalized and can move freely throughout the substance, and that leads to them having very high electrical conductivity. So really this problem here, we just needed to know the definition of metallic bonding, a little bit about how it's different from the typical covalent bonding that we learned about earlier in the course. All right, and then the next few questions we're going to go through, I guess the next 3 or so, deal with the structures of metallic solids. So one type of atomic solid where we do want you to know a little bit more detail about the structures, mainly the cubic structures, which we'll get into. The first of these deals with how these structures are generated by packing layers of atoms. So which of these correctly describes the lattice arrangement shown below? Now really the only type of cubic lattice or only type of crystal structures that we want you to know the layering arrangement as we're showing here is going to be where we're taking what are called close packed layers. So a close packed layer is when you take an atom and these sort of spherical atoms and you stack them all together like this. So in a close packed layer, you're going to have one atom surrounded by 6 others in the same layer. You're going to build this layer in all directions in 2 dimensions, and then you're going to stack these layers on top of each other in different ways to make the third direction. And when we take these layers and we stack them, there's sort of 2 ways of stacking. There's what's called ABA, or there's ABCA. And what this basically refers to, these letters, is so how many layers do you stack before? That's not a good definition. But basically there's 2 types of stacking, and what this essentially refers to is, sorry, I froze here. Alright, sorry the software froze as it sometimes does and I try to erase too much, so I'll start this one over. And so this problem here is dealing with stacking layers of what are called close packed atoms. So this is the only type of layered stacking we're really going to ask you about is what's called close packed layers, which, as I said, is going to be when you have the atoms stacked as close together as possible in a single layer, which I didn't do as good of a job of drawing it this time, but hopefully you get the idea. And so basically these different colors here, each of these is showing one layer, or at least a part of a layer, where you have, as I said, one atom in the center surrounded by 6 others. That's putting the spheres as close together as possible. And then when you take these layers, which are two-dimensional, and you want to stack them to make the third direction, you can do it in 2 different ways. It's called ABA, ABCA. And basically this is going to generate 2 different close packed structures. So ABA generates the hexagonal close packed. ABCA generates the cubic close packed. Or I guess closest is how we say it. And then ABCA generates the cubic closest packed. So both of these have the same packing density. The atoms are still packed together as tightly as they can, but it forms 2 different unit cells. The cubic close packed is more often referred to as face-centered cubic. So it's one of the types of cubic lattices that we have to know. So ABA basically means that you're going to stack one layer, you're going to alternate the second layer, and then the third layer is going to be directly above, eclipsing the first layer. For ABCA, you're going to stack the first layer, you're going to stack the second layer offset to that, the third layer is going to be offset again, and then not until the fourth layer do you actually start stacking them, eclipsing each other. So if we look at this arrangement here, what we see is that in the color coding is sort of helping us understand this. The first layer shown in yellow here is going to be called A. Second layer is offset from that, so it's B. The third layer in green is offset again, so it's C, and it's not until the fourth layer that we get A again. So this would be called ABCA. The first and the fourth layer are going to be the ones that are directly on top of each other, directly eclipsing each other. So this is ABCA packing, and as we said, that's going to then give us face-centered cubic or cubic closest packed. And so that's going to be choice C here, cubic closest packing. ABA would give us the hexagonal structure, and this is not ABA, this is ABCA. And then these other 2, body-centered cubic, is not generated from closest packing, so we wouldn't ask you really about the layered structure for this. And then for choice D, ABAC, that's not one of the options that we even have. It's either ABA or ABCA. So it's going to be C, that's the best answer for this one. And we're not going to do a lot with these sort of packing of layers as we're showing here. We're more interested in the cubic unit cells and understanding those, but there could be some questions about the different types of packing that we get for close packing, and really just knowing the distinction between these 2, ABA, ABCA, is really all we're going to ask you about. We're not going to go into too much detail there. All right, and then the next few questions deal with the actual cubic unit cells. So once we stack the layers, we can pick out cubic arrangements of the atoms that we can arrange in 2 directions. And that's, again, specifically true for the ABCA packing. And then there's some other other types of cubic structures that are not generated by closest packing that we want to know about as well. So here, though, we're not really dealing with a specific structure. We just want to know an atom located in the body center of a unit cell is shared equally between how many unit cells. So we actually went over this in the exam review, but if you didn't see that, I'll go over it here again. And so basically when we have these different cubic unit cells, there's simple cubic, body-centered cubic, face-centered cubic. There's also a bunch of ionic compounds that have cubic unit cells, but we omitted that material. But whatever the situation is, and this is what we want you to know for this part of the course, is there are different places that you can put the different atoms in the structure. So we have one place is you can put atoms on the corner. So each corner position is going to be shared by 8 unit cells. So basically if we take these cubes and we stack them like blocks in all directions, each corner is going to be shared by 8 neighboring cells, and then you're going to count that as 1/8 of an atom for that specific unit cell. The other places that we can put atoms would be, we can have the face center, so that's where we put an atom right in the center of one of the square faces. I'll put it up here to make it a little bit more obvious. So if you put an atom right in the center of a square face, that's called a face center position. And when we stack the blocks together, you're going to have 2 faces from neighboring cubes sort of touching each other. And so this would be shared by 2 unit cells and then counted as a half. Then getting different colors in here, we can put atoms on the edges. Now the cubic unit cells for metals that we would talk about don't have edge positions ever filled, but you can put atoms on the edges, and you would have seen that if we had covered ionic compounds in more detail. But the edge positions, when you stack cubes together, are shared by 4 neighboring cubes, and then they would count as 1/4 of an atom for that specific unit cell. And then finally, the last position would be to put one right in the middle. So this is completely inside the cube. Again, hard to see in 3 dimensions, but this one's completely inside. It's called the body center position. And that one is going to be not shared at all because it's completely inside of one of the cubic unit cells. So when you stack the cubes together, it's not bordering 2 or more cubes. It's completely inside of one of them. So it's not shared, and it counts as a full atom for that unit cell. Okay, so those are the 4 different positions we can put atoms. And so if you know, some of the test questions, you're going to have to basically count how many atoms are in a cubic unit cell, and you're going to have to use these rules to do it. So this one asks about the body center. And as we said, the body center is shared equally only within 1 unit cell. It occupies the main unit cell, not the neighbors, so that's going to be choice A. The body center is the only position where it's not going to be shared by other unit cells when you stack these together. All right, and then the next 2 questions deal with distances along the edges of different types of unit cells. So we're talking about cubic cells here. We're not going to go into crazy detail with the geometry. My lectures did to some extent to help you understand some of these things, but we're going to just ask you some of the more straightforward aspects of the geometry. And basically, what this question is asking is, what is the distance in atomic radii along the edge of a primitive unit cell? And so when we think about a primitive unit cell, what we're basically doing is we have a cube, and a primitive cubic cell basically means you're putting 1 atom at each corner of the cube. So a primitive cubic cell would look like this, where you have your cube and you just have 1 atom in each corner. Now the reality is it's convenient to draw them like this with a lot of space in between the atoms to sort of easily visualize where they are in the cube, but remember that these atoms are going to pack as close together as they can until they're until their electron clouds basically are up against each other. So if we look at a face of this primitive cubic cell, we see that there's 1 atom in each corner. And so if we draw just 1 square face and then we put an atom in each corner, basically these atoms are going to get as close together as possible, and so each face is going to look something like this. Now I'm not very good at drawing this, as you guys know. I'm not good at drawing anything. So let me try to do this as best as I can. So basically each atom is going to sort of border the other ones like this. They're ideally spherical and all the same size, of course, which I'm not going to do a very good job of drawing. But you have sort of this arrangement here where each corner, as we said, has 1 atom, and they're going to be stacked to each other as close as they can. And they're going to basically touch each other at the halfway point of each side. So what we're talking about here is the distance along one side of the unit cell, which we abbreviate as A. And in the primitive cubic cell, as you go from one side to the other, you have 1 atomic radius and then a second atomic radius. So basically A is going to be equal to 2r as you go from one corner of the face to the other corner along that distance. So you're going to go through 1 atomic radius and then a second one, so the total is 2r. So B would be the correct answer for this one. And then the next one is a different unit cell in this case. So we're looking this time for the distance across a diagonal of a face-centered unit cell. So instead of talking about the side distance, we're talking about the diagonal distance, or instead of talking about primitive, we're talking about face-centered cubic. So if we draw a face-centered cubic unit cell, it's still a cube, of course. All of the ones except for hexagonal are cubes, and we're not going to go into too much depth with hexagonal anyway. So in the face-centered cubic unit cell, what you have is atoms in each corner, and then the face-centered tells you that you also have one in the center of each square face. So there's 6 faces. Each of those is going to have one. A little bit hard to draw in 3 dimensions. It looks a little bit messy in that dimension, but what this is asking about is across a diagonal face. And so if we draw one face of the unit cell, again, one of these square faces, what you have in this situation in face-centered cubic is you're going to have atoms in each corner again. This time they don't touch along the side of the unit cell. And the reason they don't touch along the side is because you're also going to have an atom right in the center of this face, face-centered being the key word there. So a face of a face-centered cubic unit cell looks like this, where you have atoms in each corner. The atoms in adjacent corners no longer touch each other, but they're going to be all surrounding one atom that's in the center of the face. For example, this one here, surrounded by these 4 on the side. And this is looking for the distance across the diagonal. So if we go across the diagonal of this, which is, let me draw this in different colors so you can see it better. The diagonal distance is going to be this distance here. And as we go across the diagonal, it's going to be 1 atomic radius to go to there. We're going to go through the whole diameter of the center atom, so that's going to be another 2r. And then we're going to go through another radius of this other corner atom on the other side to give another r. So in total, the distance of a diagonal is going to be equal to 4r. Okay? So we went over in class a lot more derivations for these distances. These are probably the only 2 that you'll really want to know. I mean, some of the other ones are more complicated. If we talk about, you know, the distance along the side of this, that would end up as 2 radical 2r. We derived that in class. It's more complicated geometrically. It really is just geometry more than chemistry. But for problems like this, where all you have to be able to do is just draw the unit cell and visualize one of the simple directions, either the diagonal or in the primitive cubic cell, the side length, that's going to be sort of the types of things we'll ask you about. So it's all summarized in the notes. You definitely want to have those available on the test and make sure that you're knowing those. But like I said, it's mostly going to be, the level of questions that you see in the homework assignments. We're not going to get any more difficult than that on the exam. All right, and then finally, the last few questions I'm going to go through, the last 3, I guess, deal with phase diagrams. And so phase diagrams are diagrams where you have temperature on the x-axis, pressure on the y-axis, and they're going to be used to tell us for different substances under what temperatures and pressures do they exist as solids, do they exist as liquids, do they exist as gases, and where do the phase changes occur between those. So this question here, for the phase diagram shown, we want to know which of these will result in vaporization of X. Now, to go over the terminology quickly, we skipped one unit in the course where we would have covered this a little bit more in detail, so we do need to be a little bit aware of the terminology. So if we're talking about vaporization, that's the phase change of going from liquid to gas, or liquid to vapor, as it's sometimes called in a phase diagram. Gas and vapor are basically the same thing, so you don't need to really worry about distinguishing those. If we're talking about the opposite process, that's going to be called condensation. So that's if we go from gas to liquid, or vapor to liquid. And then melting, as you're probably familiar with already, is going to be going from solid to liquid. And finally, the other one is what's called freezing or fusion. Actually, sorry, freezing is just the proper term for that. We won't confuse you with fusion. Freezing is going to be the other process, going from liquid to solid. All right, so most of these are terms that you use in your everyday life. Vaporization, perhaps not the most common one, but this is the different phase changes we have in a phase diagram. And then the last one, which we don't always see, is called sublimation. And that's if we go from solid to gas. And this one is usually works in both directions. Sublimation would be solid to gas or gas to solid. Usually it's solid to gas. There's not really a separate term for the opposite process. All right, but in this problem, we're looking for vaporization. So that means we want to find a place where we're starting at a liquid and changing to a gas. What process would lead to that? So to do this, we need to label the different parts of the phase diagram. So you have these lines in the phase diagram. They're going to divide it typically into 3 sections. The one that's at the lowest temperature and highest pressure is going to be solid. The one that's at the lowest pressure and highest temperature in the bottom right is going to be gas, and then the one in the middle is going to be liquid. So those, we're going to just usually focus on simple phase diagrams in this course. They're going to have 3 main regions, solid, liquid, and gas, as shown. So we want to find where it starts out as a liquid. And so if we look at choice A, X is starting at point A, that's going to be solid, so that can't be right because we're looking for a process that starts in a liquid goes to a gas. Choice B, X and conditions indicated by F. F is going to be the boundary between liquid and gas. So this could be a place where we have vaporization because we're starting where anytime you're along the line, you're basically going to have both phases present together. So at point F, we have liquid and gas together. But if we raise the temperature until it gets to H and the pressure, F to H is going to go from a mixture of liquid and gas all the way to liquid. That's not vaporization because vaporization involves converting liquid to gas. So this one's not right either. And the next one here, we're at X conditions at point H. So we're starting here in choice C in the liquid part of the diagram. And then we're going to change the temperature and pressure until we get to A. But that process here, going from H to A, is going to be liquid to solid. That would be freezing, not vaporization. And then for choice D, X is conditions at point A. We're starting at solid, and then we're going to point C, which is over here in the gas. That would be sublimation. We're going from solid to gas. That one's off. And then finally, if we go to choice E here, we're starting at H, which is liquid. And then we're changing the temperature and pressure until we get to C. So we're going from H to C. That process here is liquid to gas. That's going to be vaporization. So this would be the correct answer. So if you're looking for vaporization, you want to find a process where you start in the liquid part of the diagram or any part of the diagram where the liquid exists, and then you end up in the gas or vapor part of the diagram. And that's the only one that works is choice E there. Okay. And then the other thing that we can do with phase diagrams, which is what we're asked in this problem, is we can predict the temperatures at which these different phase transitions occur. So here we have another different phase diagram, again, similar in arrangement. We have solid on the left, liquid in the middle, gas on the right. And we want to know what is the normal melting point of Y. So when we're talking about melting point, again, that's going to be converting from solid to gas. Sorry, solid to liquid, my bad. So we're going from solid to liquid. So basically this whole line here that divides the solid from the liquid, this is our sort of melting line. So anywhere along this line is going to be the boundary between those two. And then whenever we talk about the normal, either melting or boiling point, that's going to be the melting temperature at 1 atmosphere. All right, so anything normal melting point, normal boiling point, that's going to be the corresponding temperature when we're at a pressure of 1 atmosphere. Because these phase transition temperatures, they do depend on pressure, as you can see from these diagrams. So we want to find, and we're showing here the 1 atmosphere line. So basically we're looking for at 1 atmosphere where the solid and liquid are going to be intersecting each other. That's going to be right there. And this is not the most precise diagram, but if we're careful about drawing this down, we see that that's a temperature that's right below 20 degrees Celsius. And so the best choice would be D, 18 degrees Celsius. All right, so melting, we're talking about the boundary between solid and liquid. Normal melting means at 1 atmosphere of pressure. So we find where along this line here, where does it get to 1 atmosphere? That's at a temperature of 18 degrees Celsius. Okay, so that's how we read phase change. I do think part of the reason we had a little bit of trouble with these phase diagram problems is because This is the very last topic. It's the one that's not covered on the third midterm. It's only on the final. So I'm sure a lot of you haven't spent too much time going through this yet. If you go through the very last lecture video that I posted, I give you an example of almost every type of phase diagram question we can ask, and these sort of fall into those categories. All right, and then finally we're going to go to the last one here, which is the phase diagram for CO2. And we have a sample consisting of CO2 gas and CO2 solid at equilibrium at minus 78 Celsius and 1 atmosphere. And it's heated to minus 30 and the pressure is increased to 8 atmosphere. Based on this, what will happen? So we're going to find our starting point first. We're starting at minus 78 and 1 atmosphere. So that's going to be here. And we can label the regions again to help us. This is going to be solid, liquid, gas, as it normally is. So we're starting at the boundary between solid and gas, which basically means at this temperature and pressure, both the solid and the gas exist together. Whenever you're at the boundary between them, that means both of those phases can exist under those conditions. And then what we're doing here is we're heating to minus 30. So we're going to first go left to right on the temperature axis to minus 30, which would be somewhere, I guess around there or so. It's not very precise, but somewhere around there we're going to heat it to. And then we're going to increase the pressure to 8 atmospheres. So first, when we increase the temperature, we're going to go completely to gas phase. But then if we increase to 8 atmospheres, which is about here in the y direction, if we increase to 8 atmospheres, we're back in the liquid part of the diagram. So this process here of taking the mixture of solid and gas, raising the temperature, and then raising the pressure, we're going to end up with just pure liquid CO2. So the correct answer then would be choice B. All of the CO2 will be converted to CO2 liquid. And so reading a phase diagram is usually just going to involve that sort of process, looking at which temperature and pressure you're at and figuring out which part of the phase diagram you're in, either pure solid, liquid, gas, or the boundary between the two, in which case two phases can exist. And then what none of these problems dealt with would be you also have what's called here the triple point, where all three of the lines intersect. That's going to be where you have all three phases, solid, liquid, and gas, together at the same conditions of temperature and pressure. Okay, so that was just sort of a quick overview of some of the more difficult phase diagram questions that we had and that we had the lowest success rates on. There's a lot of other types of those problems on the homework assignment and other topics that were covered in this unit. So if there's anything else you have questions on before the final exam or very last minute before your exam today, please get in contact with me. I hope you guys found some usefulness from these videos. I was happy to put them together and see that people were watching them. This is the last one, so I'll be in touch with you other ways. But hope you all have a great rest of the semester. And again, please stay in touch with any questions you have.